I'd like to explain a cute trick I discovered to literally write truth tables as non-negative integers in base 2 in their natural order, and how to count the total number of all possible functions which take as input n Boolean variables and produce as output a single Boolean variable. If this doesn't make sense to you at this point, then don't worry. The purpose of this video is to explain all of this, and hopefully by the end it will all make perfect sense. Let's begin with the following definition. You may already be familiar with the binary Boolean operators AND and OR. For example, AND returns 1 if and only if both of the input variables are 1, and it returns 0 otherwise. Whereas OR returns 1 if either or both of the two input variables is 1, and 0 otherwise. Our goal in this video is to obtain the well-known result that there are exactly 16 binary Boolean operators, and our approach can easily be generalized. If you are familiar with computer programming, then you already know what a Boolean expression is. Let's take a quick look at the Math Inspector source code. As you could see, there are a number of if statements here. We could, for example, write if R and not R print, this will never print. By definition, a single Boolean variable can take the values of either 0 or 1. And in the language of logic, 0 corresponds to false and 1 corresponds to true. If A is a Boolean variable, then an example of a Boolean expression is not A. This has the following truth table. Another example involving the Boolean operators AND and NOT, which acts on a single input Boolean variable, would be A and not A. This Boolean expression will always produce an output of 0 or false. Can you see why? This means the Boolean expression A and not A will always output 0. The reason for using truth tables is this approach completely sidesteps needing to deal with Boolean expressions at all. This is very important for obtaining a complete classification. That's because there are infinitely many Boolean expressions that all correspond to the exact same truth table. And if that's not clear, then please prove it as an exercise for yourself. In this case, we have seen that, for example, the Boolean expressions 0 and A and not A are different Boolean expressions that both share the exact same truth table. Let's begin by considering the case of n equals 1 for a single Boolean input variable. In other words, let's consider the collection of all functions of the form shown here from 0, 1 to 0, 1. In this case, there are two possible input combinations, namely 0 and 1. Therefore, we can obtain a complete classification of all possible Boolean valued functions which act on these possible input combinations by forming the so-called truth tables. The functions shown here are the only 4 possible such functions. They are the functions 0, identity, not, and constant. We can also define these 4 functions as a sequence of symbols x, y. That's because every Boolean function f is defined by a collection of rules which corresponds to an ordered pair of symbols x, y, where x and y can take the values of either 0 or 1. The figure shown here shows how these 4 functions act on the underlying set of 0 and 1. Let's now turn our attention to the case of two input Boolean variables. The binary Boolean operators are functions of the form shown here, and our goal in this section of the video is to obtain a set of all possible such functions and show that there are exactly 16 of them. In this case, there will be 2 squared or 4 possible input combinations. These are 0, 0, 0, 1, 1, 0, and 1, 1. These happen to be the truth tables from the previous step of n equals 1, but that's not always going to be the case. Anyway, there are going to be 2 to the power of 4 or 16 total possible truth tables. Let's see this. Since each truth table can be written as a finite binary string of length 4, it's easy to see that there are exactly 16 such possible finite binary strings. This completes the proof that there are exactly 16 binary Boolean operators. But let's take a look at some examples and make sure we really understand what's going on here. If the diamond symbol shown here is an arbitrary binary Boolean operator, this means that the diamond operator assigns an ordered pair of Boolean variables x, y to the Boolean variable z. We can write this as z equals x diamond y. We have already considered the two binary Boolean operators and or, and their truth tables are shown here. The next operator I'd like to consider right now is called implies. Let's take a moment to observe that if x implies y is true whenever x is false, then this captures the idea that it's possible to prove anything if you start from a false assumption. Okay, so just as we did for the case of a single input variable, we can form a sequence of 4 symbols w, x, y, z to represent the truth tables for these operators. Let's once again show that there are exactly 16 distinct binary Boolean operators. Every such operator corresponds to one of the truth tables in the collection shown here. And by listing these truth tables in their natural order and counting their number, we find that there are 16. This is what I call the truth table theorem. It says that for n input Boolean variables, the total number of distinct truth tables is exactly 2 to the power of 2 to the n. Feel free to pause the video and make sure you understand the proof. This truth table theorem provides a complete classification of all possible Boolean valued functions for any number of input variables. Or alternatively, it provides a complete classification of all possible finite Boolean expressions. The two most interesting things about this approach, in my opinion, are on the one hand, it enables us to write the truth tables in their natural order. And on the other hand, it's the exponential explosion in the number of truth tables as the number of input variables n is incremented. This approach also provides some interesting insights into the non-negative integers from a very unique perspective. And this kind of multiple perspective thinking plays a really important role in mathematics in general. It's not that one or another perspective is better than the others, but rather each different way of looking at things provides valuable information about the underlying mathematical structure. And these different perspectives complement and reinforce each other, and they help us get a better idea of how the mathematical machinery actually works. I'd like to end with one more diagram. A really useful perspective for thinking about a collection of functions, like our truth tables, for example, is to abstract away the underlying sets or symbols that these functions act on, and just represent everything with a diagram where you connect functions together with arrows to show how these functions are related by function composition. One way of interpreting this picture is, without anything else, the symbols 0 and 1 are completely meaningless. It's only the composition rules that give them meaning. But since the choice of the symbols 0 and 1 was arbitrary, the only thing that really matters is that they are different and that there are only 2 of them. By removing the underlying symbols, we have gained a deeper insight into the mathematical structure itself. Okay, so that's all for today's video. And don't forget, please, to like the video and share the link with your friends on social media. I would really, really, really appreciate it, and it's one of the most helpful things that you could do to help my channel grow. It's really great to be back on YouTube. Please subscribe to the channel, click that bell icon, enable notifications, as I'm planning to upload a number of new videos soon. Thank you so much for watching until the end. I wish you the best of luck in all of your mathematical and non-mathematical endeavors, my friends.